All right. So since my last videos, I think I went into a lot of detail of how I would approach calculations. I don't think I want to go through too much detail here, but want to show where I started working with a very simplified hydrofoil. So right here is what I've got. It is incredibly simple geometry. It's a really simple airfoil or hydrofoil for the mast. 3 feet. It's in the dead center of a fuselage, which is also 3 feet long. And wingspan here, we got a meter, and we got roughly half that size here. And this gives you, overhead plan area of 1,000 centimeters squared, and this gives you, I think I've set it at 200. And so what I want to do is kind of go over what I explored here. And so I really started with hand calculations. That's how I like to approach almost any kind of engineering design problem. I want to make sure I understand things. It really helps me get what physically is happening in my head and have some level of expectation. I have some level of expectation of how things are going to behave. And so I put that down in hand calcs. Then I either see how that works in a finite element program or whatever model I have available. Sometimes I have, something built available, but oftentimes in big design problems, it's mostly, some kind of computer simulation. But to keep things easy on myself without going to the difficulties of composites and everything so far, I kind of want to get a bigger picture of things. I did assume that this hydrofoil is solid aluminum, the fuselage, the wings, the mast, everything. Any kind of bending mode I looked at. So I looked at bending modes with beams. I looked at torsional modes of beams, and I also looked at shear modes, but shear didn't seem to matter too much for this problem. All done with aluminum and all analyzed with rectangular shapes that are the average thickness of the airfoil I had, or hydrofoil. I assume it's fixed at the board. I assume that any vibration, there's no added mass from water. I can account for that later. And I didn't really look at the fuselage modes too much. I did kind of play around to see if they have an effect, but it seemed to matter more for higher modes. But as you can see, a lot of hand calculations. And what I found out was there are a lot of combined modes for various things. And so I'll go over the models I created. So one is pretty simplified. It's like a tet mesh model. It does have the airfoils in there, and sorry I'm zooming it around, but it does have the hydrofoil shape in there that I modeled in CAD. I don't think that's a really good hydrofoil shape, but it was simple to model. I just wanted to get something going, and I looked mainly at these modal shapes. And what you'll see is that this first lowest mode, given the dimensions I had, this is roughly 3/4 of an inch wide at the thickest. I think it's half an inch back here, and so I use the average of those two as the dimension. Actually, I can measure here with this program. Let me do that real quick to make sure I'm not a liar. I like to make sure I'm correct. So measure from here to here. Actually, so that's an inch across, and so the average is actually 3/4. So it's an inch across. It's half an inch in the back, and so the beam I used was just a rectangular beam to approximate the mode of this. But so I did this FEM model or finite element model, and I got this bending mode. You can see here. So that's the first mode I hit, and by hand, this is the easiest one to calculate. I did have to play with some of the inputs a bit. Anytime you do vibration, you do end up needing combined modes, and it's best to not have to do any kind of fudge factors. I don't like fudge factors. It means you don't really know what's going on. But so FEM says 8.423. I think that's what I put in here. 8.423. By hand, oops, sorry, wrong program. By hand, I got a little bit different than that. So the mast bending, what did I get? 9 hertz, like almost 9.1 hertz. And so that's within 8%. And what I also combined there was I combined another mode. Let's see, what was the mode I combined? Combined bending mass. Ugh, I'm having a hard time talking for some reason tonight. there we go, combined bending mass. So it's actually a combination of not only a bending mode, but a torsional mode or a twisting mode of the shape. So not only do we get the pure bending mode, like a pure bending mode, but there's also this rotation and torquing of this whole moment of inertia of that fuselage and the wings combined. So the mass and everything is causing that mode to drop. And so when I combine those things, so not only the torsional mode, let's see, combined bending mass, I combined the mass in moment, which is what that is. I also looked at a slight torsional mode of the mass because it's not a clean side to side shape. You know, if you look at it, there's a slight, let me get dead on top. Let's see, which view do we have? You can see that the front wing has got this slight torsional twist mode to it. So I combined all those modes by hand, and I got within, 5.6%, 5.5%, something like that. I say that's pretty good, considering the simplifications I made, just trying to see what was going on. So I got 7.9 hertz by hand. The model was 8.4 hertz. I say that's pretty good. Second mode, I looked at this one here. So this is a torsion of the mast itself. So this is a lot of just the mast twisting. And I got 19.67 hertz in my finite element model. By hand, 19.67, 19.69, depending on the, I was playing with the mesh density a little bit. And I got within, 7% of that. So that's pretty good. And the first one, I think, that showed the flapping of the wings, or just there we go. So there's this flapping of the wings mode, or twisting of the mast itself with the wings. And I think the reason we're seeing this mode, I don't think this is necessarily one of the first modes you see on a real hydrofoil. I think we are seeing this is because this is a very simplified model. We have this thick piece of aluminum going all the way out for a meter. It's not tapering down, so you have a lot of mass out here, so it's actually causing the fuselage to twist around. And so it's a simplified model. I'm just trying to understand what's going on here. So it's really the combination of the modes of the mast and the front wing wanting to bend together. And then a little bit of a mode after that is actually more of a pure wing flapping mode, of where you get this wing doing this flapping motion. Let's see if I can get a dead-on view here just a little bit. I like this program. It wasn't that expensive. It's just the navigation and the scrolling for Zoom isn't that great. But yeah, the other mode is almost a pure wing flapping. So that's 37.3 hertz. And I got by hand within 3% of that. I would say that's pretty good. And the last one I really bothered with was the fifth mode, which was, you're starting to get these higher modes where the mast is actually combining this motion with the wings actually not participating as much. Or you notice as the mast goes forward, the tips will kind of want to stay where they are, and so you get a rear wing flapping. You get the mast bending forward, and when I calculate by hand, when I combine these things, I got within like 8.5%. If you look at combining these modes, I say that's pretty good. Another thing that I did that was, I think, helpful was this mode right here, or this model was, I took a completely stick model of them, and I really like making stick models, and I found out I could actually do it with this program. I've done it a lot in ANSYS and Abacus. Actually, more in Abacus, but also in Nastran when I was working in the aerospace industry. There are a lot of stick models like this built, where we actually built all the models by hand. And so what I did was I gave this a pure rectangular beam properties of the model. And so let me see if I can show. There we go. So these are the actual simulated shapes. And you'll see these are pure rectangles simulating what's going on. These have no airfoil shape whatsoever. They're just the average thickness here of the airfoils. And what that ends up with is, because the real model oops, the real model here is, let me turn that back off. This connection point, for instance, at the front wing is dead center of that fuselage. And so I did not account for the fact that when you join this right here, the fuselage doesn't extend all the way forward because the node just ends, and the wing actually starts right in the center. So it kind of gets a little higher mode on a little lower mode because the wing's longer. It's actually attached to that mode. So you could do there's some things you could do to like change this model to make it more accurate in that area to kind of fudge it, but I didn't bother. I just went ahead and just analyzed it. And so what you'll see is that you get these similar kind of modal effects with similar magnitudes, but they're fundamentally different because you don't have that airfoil shape that's not accounted for in this model. But so at first mode 7.9 for the airfoil, I got 8.4. For this beam mode, I got 7.9, and then my hand calc was within like 0.5% of that. So that's just telling me that my hand calc is correct. That's not necessarily saying that I have a good representation of physical reality or anything. It's just my hand calc's correct. Second mode, we see a similar thing when we do combined effects, like either that's torsion mode of that mast. You then end up with 18.4 hertz. With my hand, I got within like a really small amount. I was actually amazed how close this got because how simple that torsion calc was. Within 0.05%. It was really, really close. And third mode, I'm just going to go ahead and go through all these first 5 modes, was also this combined twisting of the mast, just kind of bending from torsion of the fuselage of the mast combined with the flapping of the wings, which drops it from the pure flapping mode of the wings. So I got 24.96. Was that right? 24.96. Just making sure my numbers right. So I got within 5% of that. That's good. Same thing with, I think we get a little bit more divergence when we start getting higher modes because it's harder to understand all the different effects. The pure flapping mode, and this is where I'm talking to you about that models of implication where you don't have the full length of that fuselage here because that node just stops here. So your wing mode is going to be lower in this model than it would be in reality because you don't get that added stiffness of that attachment here if it's really attached. That just depends on how your model is versus reality. But 28.93 hertz and got within 7.5%. And of course the last one that we're going to go over is mode 5 where you get this forward bending mode. So the modes are very similar between the pure stick model of just beams versus the TET mesh. But what that's telling me is that with all these things going on, even with this heavy front wing, heavy rear wing, and completely unoptimized fuselage of roughly the size, if you took like a starboard, IQ foil, or 1,000 centimeter squared wing, which is a little bit bigger than IQ foil. But if you took that and you run the analysis with this heavy front wing, your mast mode just dominates. Like that first bending mode, and you can feel that flop some too when you hold your mast. You can bend it by hand. I mean, you can feel it flex. So that stiffness there is very important. And the next one is that torsional mode. Now, I think that these would be improved greatly when you account for the fact that you would get some kind of carbon composite where you get some stiffness without so much of the weight. And so you would increase the fundamental mode of these a little bit. I don't know how much. I'd have to go run the numbers. I didn't do that yet. But this kind of shows you that why mass is so important on these things, especially at the wingtips, because you get all this moment of inertia out at the wingtips. And I had to calculate the moment of inertia of these shapes. And they're simple shapes. That's why I kept them simple, just for this demonstration, trying to understand what's going on, which is, I think, is always a good way to start analyzing a problem, is just simplify everything to try to understand fundamentally what's going on. I don't expect these modes to be exactly the same at all when you look at a real carbon fiber, stiff, light wing, but this indicates kind of the direction that things are going. I also noticed that when you get to these higher modes, you get a rear wing mode, you get a few of those, you start getting twisting of the fuselage stiffness, it matters. But I think This one, if this is a real mode, I'm not convinced it is because of how heavy the front wing is, but you see that the fuselage is bending up and down. These are the ones where you start to get a crazy interaction with the fluid flow, because when this fuse, I mean, it's not going to bend up that much in reality. It's going to bend a much smaller angle. This is exaggerated. But with this bending up and down, you're going to start getting this effect of the flow over this starts changing. So when it bends up, it's going to increase the angle of attack of that front wing and push it up further. Then it's going to snap back down, and then it's going to bend downward, and it's going to get this angle of attack pushing it opposite of lift. And what you get is this flutter situation, or like you get an aeroelastic effect where your deflections of your foil start interacting with the fluid, and it causes bad things to happen. I mean, it tests airplanes for this. Control surfaces have a problem, but I don't know how huge this effect is on hydrofoils. I know that it's a potential effect. I don't know how significant it is for real hydrofoil design. I just know it's there. I just know it's something that you could potentially run into if you are moving very fast in the water and you have a fuselage, mast and wing system that is not stiff enough. And it also happens with, maybe not that one, just rear wing effect. I think it was around mode 15. Yeah, that's not quite what I was thinking about. Where you get a torsional mode. Okay, this one. This looks really ugly because there's a twisting effect going on with this wing, and I think you actually see it better with the actual mesh of the TETs, because this model, it's pure beam, so it looks kind of silly. It doesn't really animate that well. But when you look at the TET mesh model, similar mode, you get down to the mode 1450, these higher mode shapes. Yeah, it's always interesting to see it dance. Maybe I don't know if I have the results saved with that 16th mode, but you do start seeing this more torsional effect in the higher modes. And I think that's more where you get like the classical aeroelastic effects of these things interacting with the fluid flow. Or maybe this is the twisting effect. Maybe that is the mode we're seeing. Yep, that's the bending fuselage. So you can see the wing twisting. Obviously, this scale is exaggerated. I could stop this and kind of look at, let's see here. Let's look at a scale. So the scale factor is 0.1. So let's be 0.05. Let's give it half that scale. And we'll reanimate that. There we go. So I changed the scale because that's completely under my control, because the thing about modal shapes is this is purely the direction of the shape. It's kind of what the shape looks like. It doesn't tell you anything at all about the magnitude, because I'm not forcing this vibration with, a certain force. It's just, this is the shape it's going to want to assume given this frequency. So to really see how much it would deform, I would need to know the force of the water on it. I would need to know all kinds of things, which I'm not doing right now. So I'm just looking at, here's a shape. But you can see the twisting of that front wing with the fuselage. And so that is where you get that interaction with the water flow over this. So that's where I got with the mechanical look at this model. I think that also you could look at the stresses. I'm not too bogged down in the stresses with this, because I think that in this case, I'll probably check it at some point, but in this case, I really do think that the stiffness of the fuselage, the wing, and the mast completely dominate the equation. I think that if you make these stiff enough, they're probably strong enough to survive. Now, where that is not the case is where you have these connections from like the mast to the fuselage, from the fuselage to the front wing and rear wing. That's when you really need to know the loads. You need to know if the fasteners are going to work right, if the load is passing through at the joints, where the joint design becomes important. I think that really starts to matter. But for the gross deformation of things, stiffness just dominates the equation. Just, are you even in the right ballpark of this thing? And you need to solve the stiffness problem first. That's almost always the case. Unless you're sizing like some kind of lifting feature where you're lifting something that has to be a certain strength, and strength determines things. But a lot of time it's stiffness. For functionality of mechanical components, it's almost always stiffness. Like cars, you worry about the stiffness of the suspension, the stiffness of the springs, the engines, the stiffness to certain things. I mean, strength does matter, but you have to look at both. You can't just look at strength. So I didn't look at the stresses of this. Mold shapes don't tell me anything about stresses right now. I think it's going to be fine, but I will check it at some point in case you're just wondering about that. But I went through, got hand calculations, and did some finite element runs with this finite element program I got, and it's just the mechanical side of things, because I'm more familiar with mechanical. I'm comfortable with it. I'm going to approach it. But then after that, what I want to do is start looking at the hydrodynamic, or just basically the fluid flow of this, the lift, probably stability, because the program I found can actually look at that. That's coming up next, and it's taking me some time to make sure I'm comfortable with enough of the program that I understand it well enough to show it. But I want to approach that next, and kind of convey that anytime you come into a mechanical design problem, it's good to have a holistic understanding of all the effects. That's very contrary to what happens in a lot of industry, where you have a stress guy, or you have a finite element guy, you have an analyst guy, you have a fluids guy, you have a thermal guy, you have a vibrations guy. But to solve a real design problem, when it's anything new that you're created and you're forging new ground and new territory, you need to understand the bigger picture. And I really like to make sure I understand that, and I hope that you do too. But that's what I just want to show here. But I think that's all I've got to talk about today, and I hope you enjoyed this, and hopefully see you later.